So I'm in the lucky position here where I get to follow Bjarne in a conference focused on C++. We'll see how that goes. What I'm talking about here is the work of many people actually who together ended up basically adding threads to the C++ language in C++ 11. I've mentioned a few of those here who've actually worked on the memory model. I'll say a little bit about the Threads API, but I see that Bjarne already actually covered that about as well as I was going to, so we'll see. I'll focus mostly on the memory model here, and in order to understand the memory model, we have to talk about data races, and we have to talk some about atomic objects. So that's really sort of the core of this talk. So what are threads? I suspect everybody knows that here already. So when we talk about threads, we basically mean about essentially multiple instruction streams or programs executing together, sharing objects in the heap, sharing variables, and the like. We'll assume, and C++ 11 requires that static variables and sort of everything that they can possibly point to is shared between threads. So all the memory is shared. Each thread does have its own stack and thread local variables. Why are we talking about threads? Well, certainly threads are not without controversy. If you try Googling for the phrase threads are evil, when I first tried this, I got about 18,000 hits. Last I tried it just before the talk, it was up to 25,000. So clearly not everybody likes threads. On the other hand, they've historically been a very convenient way to deal with multiple event streams, to write responsive GUIs and the like. And as they've recently become sort of the dominant way to take advantage of the multi-core processes that we're increasingly getting in our machines, sort of in lieu of additional single-core performance. So they're everywhere. If you ask on a Windows machine, if you ask Task Manager how many applications are using threads, last I looked, there were almost none that weren't. So let's say a little bit more about what we mean by threads. In order to understand the memory model issues here correctly, we'll have to refine this. But for the time being, I'll start with a really simple and sort of traditional view of what threads are, which is that I'll view threads as these sequences of instructions, one sequence per thread, which are executed just as though they were interleaved, as though I sort of basically time slice on a single machine, though that's not actually the way they're usually executed these days, run basically at each point, decide which thread I'm going to execute from next, and sort of take its next it takes its next step and execute that. So if I have these two threads here that are up on the slide, they might be interleaved. They might be executed as though the instructions were interleaved in the way that I said at the bottom of the slide. Always the value I actually get when I access a particular variable is the last one that was stored there in that interleaving. So in the example I have here, where you see R1 equals X, that's going to see the value of 1 that was assigned to X just before, 2 steps before in the interleaving. So threads in C++ 11. Well, finally, unlike C++ 03, threads are finally part of the language. It actually turns out that's not just true for C++ 11, it's also true for C11. That takes several different forms. There has to be a threads API. There has to be some way to create threads, and as we'll see, provide for mutual exclusion. There is such an API in C++ 11. There's unfortunately a different such API in C11, but that's a different story. The API that we use in C++ 11 is essentially evolved from the Boost Threads library with some refinements. And I'll say a few words about how that works, or a little bit about how that works. No matter what the threads library we use, even if we're going to use one of the pre-existing library interfaces to create threads, there's a more fundamental issue which actually affects compilers and the like, which is what do shared variables mean? How can threads interact? So far I gave you this really simple view. I'll tell you that that's not quite the full story. So we need to answer questions like, when can a particular thread see an update of a variable that's performed by another thread? Is it okay to access variables simultaneously from different threads? And connected to that, there's an atomic operations library in C++11. In addition to that, there are a whole bunch of other facilities in C++11 which are there to support threads, which I won't get a chance to talk about. So there are condition variables. There's a mechanism for performing some action exactly once. I already hinted that there are variables that are local to threads. Constructors can now, file level constructors can now execute in parallel. Function local statics are guaranteed to be thread safe and so on. But these are things I won't really have time for. I just wanted to mention them here so that you knew what else to look for. So let's start with a sort of really quick review of the Threads API. So I think Bjarne already mentioned this largely. So there's a thread class which encapsulates a thread. You can construct one by passing it a function to execute. And there's one mistake on the slide here in that the constructor there is explicit. You can then, as we'll see, when you're done with it, you can wait for the result by calling join. There's also a detach function, which, for reasons I'll explain, to first order of approximation you shouldn't use. And there's a way to ask about the identity of the thread. My canonical example here is what's often used in order to illustrate such things. It's also sort of the worst possible example of what Bjarne just said, that you should be careful about your algorithms. This, I think, is the only example that has the characteristic that, at least depending on how you measure it, is a double exponential slower than the actual algorithm that you should use. What we do here is this is a very simple illustration of how to use the Threads API to create a helper thread to speed up the really dumb algorithm for computing Fibonacci numbers. So in order to compute Fibonacci of n recursively, we have to compute Fibonacci of n-1 and Fibonacci of n-2. Typically, that's done by computing each one of them sequentially, and then adding them together to compute Fibonacci of n. In this case, what we do here is slightly different in that we notice that those two computations are independent and we can run them in parallel. Though we're going to create another thread to compute Fibonacci of n-1 while we're computing Fibonacci of n-2 in our own thread. So if we have multiple cores available, we can use them, one to compute Fibonacci of n-1, the other one Fibonacci of n-2. So in this example, the way I do it here is I declare two local variables, fib1 and fib2, to hold the results of Fibonacci of n-1 and Fibonacci of n-2. I then create a thread which, as its argument, takes a lambda expression, which is a new C++11 construct that allows me to define a function, to write down an expression that evaluates to a function object, which, when invoked, computes Fibonacci of n-1 and assigns the result to Fibonacci of 1. I've defined the lambda expression here so that the fib1 is passed by reference so that I can actually assign fib1 back to the fib1 variable in the parent. I then compute fib of n-2. I wait for the thread by joining it and then return the sum. This is actually this code has some brittleness to it that I think we would really rather avoid. So in particular, there's a really subtle issue here with doing something like this, that really nasty things potentially happen if during the evaluation of fib of n-2 here in the parent thread, with the fib of n-1 computation going on in the background, fib of n-2 throws an exception. What happens at that point is the parent thread is going to essentially go away without joining the child thread, and the child thread will continue to later write to fib1, which isn't there anymore, which is quite nasty. So this sort of thing is potentially tricky. Actually, it turns out C++11, unlike Boost, handles this in a somewhat better way, but it's still a subtle issue. So there's another way, as Bjarne already hinted. I can go ahead and instead of explicitly creating a thread, I can invoke async to just run a function that computes Fibonacci of n-1 in parallel and returns its result rather than assigning to a variable in the other thread. I can wait for it, and then at the end, I can wait for it by calling get on the result of this async call, which is a future, which provides a get operation that allows me to wait for the result. So at the end, I wait for the result, add it, and return the result. The basic rules here are, again, you always, at least to first order of approximation, want to call join or get in order to wait for one of these threads you've created to complete. The language provides other mechanisms, but we'll see later that there are reasons that those are actually very tricky to use. There's actually one mechanism, and this is what I hinted at before, that's different from Boost threads, is that we actually we basically require that you either call join, that you call join before you destroy a thread. If you forget to join a thread before you destroy it, the application invokes terminate. And the reason that's done, even though that seems strange initially, is that it avoids the problem that I talked about in the first version of the example of the child thread writing a result to the parent thread, which is no longer there. At least we notice what happened there. We notice that his thread is still outstanding, and it's about to do something nasty. So we call terminate at that point, hopefully allow you to debug the process rather than really weird things happening later. For real applications, for sort of any real application using threads, just creating threads generally isn't enough. We also need to have some way to provide mutual exclusion. So if we want to do something really simple, like increment a counter variable, and we want to do that in more than one thread, just writing x equals x plus 1 in two threads where x is a shared variable, a variable shared between them, isn't going to cut it. Because in real life, the statement x equals x plus 1 is actually not, even in the best of circumstances, is not a single action. It involves loading the variable x, adding 1 to it, and storing it back. And those are separate actions. So effectively, this will be executed as described on the bottom of this slide. Each one of these involves several steps. And they can easily be interleaved, as I showed on the bottom of the slides here, that, for example, if x is initially 17, both threads will read a value of 17, and then both threads will read back a value of 18, so I've just lost a count. So we need to have some way to prevent that from happening. And the typical way we do that is with some mutual exclusion mechanism. We somehow have some way of limiting of controlling things so that only one particular thread can execute a section of code at a time. So we limit shared variables access to x, for example, to one thread at a time. And we do that by making it acquire a lock and allowing only one thread to hold a lock at a time. So for example, the way that works back in our interleaving view of the world is we would actually write this code by acquiring a lock before we increment x and then unlocking it, releasing the lock at the end. What that effectively does is it restricts the interleaving so that the only interleavings are the ones where the lock happens after the preceding unlock. Which means that the only interleavings that are allowed anymore with the lock and the unlock in place are the ones that I've shown at the bottom of the slide here, where one thread essentially runs first and then the other thread runs to completion. So I'm guaranteed that x is incremented by 2 by the time I get done. So C++11 has a mutex class which which implements this sort of lock, which basically works as you would expect. The important thing here is it has lock and unlock operations. There's a recursive mutex class which allows me to acquire a particular lock by one thread multiple times, so long as I then release it the same number of times. If I write the counterexample correctly with the C++11 mutex class, I would acquire the mutex beforehand by locking it, increment x, and then release the mutex. This has a problem, as Bjarne pointed out, is in that the lock is not released if something inside the critical section throws, which is unlikely if I'm just incrementing a variable, but otherwise is certainly a concern. So there's another construct, or in fact two. Bjarne mentioned the other one. There's a simple version called lock guard and a more complex version called unique lock, which use RAII, as you should, in order to acquire the lock when one of these lock guards, acquire the mutex when the lock guard is constructed, and release the mutex in the lock guard's destructor. So a better way to write the increment operation is this way here. So rather than explicitly locking the mutex, I construct a lock guard with the mutex as an argument, and then when the destructor for the lock guard is called at the end of that block, the mutex is implicitly released. And unique lock, which Bjarne mentioned, is a generalization of that. So that was sort of the really quick overview of the Threads API. But in order to program with threads, really the core issue is what does it really mean to access shared variables? So let me explain why that's really an issue. So again, so far we have this really simple view, which is what most people usually start with. And in fact, until very recently, a lot of research papers also started with this assumption. On the other hand, this interleaving-based view of the world actually, it turns out, gives you properties that are really stronger than what you can meaningfully use, and it does so at a great implementation expense. Let me sort of explain the implementation expense argument here first, or the implementation expense issue. So this is a well-known example in the memory models literature. If you take There's a well-known algorithm called Decker's mutual exclusion algorithm, which lets you implement mutexes using only shared variables, which is something you should never do anyway. But if you take sort of the core of that algorithm, you can distill it down to this. So what happens is that we have two threads, each one of which essentially sets a Boolean variable, in this case assigns 1 to an integer variable, which is initially 0, and then it reads the other one. And in the interleaving-based view here, I'm guaranteed that one of those assignments of 1 to a variable has to go first. It's a consequence of that the other thread, whichever thread didn't do that, is guaranteed to read a value of 1. So from that, we can conclude that it's impossible for R1 and R2, which I'm assuming here are local variables associated with each of the threads, which are not shared. And this will be my usual convention that X and Y are shared variables, R1 and R2 are local variables. Think registers here. So you can conclude from that I can't have both R1 and R2 0 by the time I finish. Because, again, one of these threads must have assigned 1 to the shared variable first. On the other hand, so in our interleaving-based model, this can't happen. R1 equals R2 equals 0 is impossible. On the other hand, in the real world, this happens all the time. And we would like it to continue to happen because there are important optimizations that rely on that. So for example, no matter what mainstream hardware you use these days, it's quite likely when you actually store into a variable that what you're actually doing is you're writing a value into a store buffer, which is in that particular core and which nobody else can see, and then you merely go ahead and execute, you're going ahead and executing on that particular core. Still no other core can see that, and eventually the contents of the store buffer become visible to everybody else. So what that means is that it's quite possible that both of these threads actually assign 1 to the shared variable. Nobody can see that. They go ahead and read the shared variable, and they still see the original 0 value because the stuff out of the store buffer hasn't made it to memory or the cache, even the cache yet. So hardware likes to do that. It also turns out that compilers really like to do loads early because it gives them more time, it gives the code more time to wait for the result of the load. So they would really like to reorder the instructions in each thread, and it looks like that's perfectly safe because the two statements don't interfere with each other. They don't conflict, is the terminology we'll use in a second here. So there's a performance reason for allowing that. It turns out there's also a usability reason for not insisting on such things, because it's actually really hard to define what this interleaving-based semantics means if we really look at the details. In particular, we've been kind of sloppy about what it means to interleave these steps. In real life, these steps are memory accesses. The individual load and store operations that the hardware executes that end up getting interleaved. But the programmer shouldn't have to know about this. So what happens, here's an even simpler example, one statement per thread. Thread 1 assigns 300 to X and thread 2 assigns 100 to X. Now what happens on a machine that only has byte-sized accesses? Well, in that case, each store consists of at least 2 individual byte store operations. In the bottom of the slide here, I've shown an interleaving of stores to the high byte and to the low byte of X by each of the threads. So the final result here is that X is equal to 356 on this byte at a time machine. Most programmers would probably be surprised by this, and even though we're using interleaving-based semantics here, the result isn't particularly useful. In general, actually moving up a level, even if we had sort of statement level interleaving, that's not particularly useful. We really want to talk about, when we think about threads interleaving, there are just way too many possibilities of individual statements interleaving. So we don't want to think about it at that level. We really want to think about sort of larger sections of code interleaving. And it turns out the C++11 memory model gives us a way to do that. So the way the memory model really works is not this pure interleaving-based semantics. So that's an important foundation here. So what we really say is that 2 memory locations conflict if, sort of in the simple sequential view, it matters which one goes first. So it matters which one goes first if one of the accesses writes a variable that the other one reads, or if they both write the same variable. And it turns out there's a footnote here associated with bit fields, which are a little bit special. We then say, once we have this notion of conflicting accesses, accesses where the order matters, we say that two memory accesses participate in a data race if, first of all, they conflict, and secondly, they're executed by different threads and can occur, and there's nothing to prevent them from occurring simultaneously, which means we really haven't specified which one goes first. We can sort of make that precise in the interleaving-based model by saying that they can appear next to each other in the interleaving, and they correspond to different threads. We then say that a program is data race free if there's no way we can get a data race. The basic rule for programming in C++11 is that we promise the interleaving-based semantics, what's also called sequential consistency, but we only promise it for data race-free programs. So for programs with data races, in fact, the language specification says all bets are off, undefined behavior. So often this is referred to as catch-fire semantics. If you have a data race in your program, your machine is allowed to catch fire. Though if there are any hardware architects in the audience, we discourage that. The way you prevent data races, the way you enforce ordering to make sure that these things can't occur simultaneously is you use mutexes, which we've already specified, or possibly in the future, the other constructs people are considering, like atomic sections. In C++11, you use mutexes. Or you use C++11 atomics, which I'll talk about later. In addition, actually, something I won't talk about much in this talk, there are actually ways to, even for data race-free programs, to relax the interleaving-based semantics if you sort of want the last little bit of performance on existing hardware. But I'll just mention that briefly at the end. So if we look back at the Decker's mutual exclusion algorithm, in real life, if I just write this with x and y declared as ints, for example, this has a data race. Clearly, both x and y can be read and written simultaneously. There's nothing to order those. So in C++11, this really has undefined behavior. And we'll see later we can get out of that by using atomics. I should emphasize here that when we say undefined behavior, we really mean it. So a lot of people think that when they program with threads, if there's a data race, well, it's kind of unpredictable. If there's a data race, it's unpredictable which value you'll actually see. Things are actually much worse than that. So here's a sort of here's an example which I think is unlikely to occur in practice, but nonetheless is illustrative of what happens. If we have a piece of code which checks that x is less than 3, and then has a switch statement with 3 cases in it, corresponding to all the cases that are still possible after the x is less than 3 case, our compiler is fairly likely to, at least if the switch statement were actually a little bigger, compile this to a piece of code that will use the value of x to index a branch destination table, and then branch indirectly to that address in the table. Since I check that x is less than 3, it's perfectly acceptable for the compiler to conclude, well, x must be less than 3. There's no reason to do a bounds check on that branch table when I compile the switch statement. So, but now what happens if there's actually a data race? Well, what can happen between my test that x is less than 3 and the switch on x? The value of x can actually change to 4, let's say. Well, what happens then? The compiled code will actually look up 4 in the branch target table, in the branch destination table. We'll get some piece of garbage that happens to be there because that's out of bounds for the table, and we'll merely go ahead and branch there, which isn't likely to give you good results. So this is the sort of thing that really can happen if you introduce data races. The nice thing about prohibiting data races is that we can reason at a fairly high level about interleaving. Now, we don't have to reason about interleaving of individual statements. So basically what happens if we if there are no data races, we can ensure that sort of any section of code between synchronization primitives, where synchronization primitives are mutex locks, unlocks, atomic operations, and the like, any piece of code in between there looks like it executes atomically. I can't visibly see that another thread is doing something in the middle there and interfering with it, because another thread that could see that I'm in the middle of such a section which has no synchronization in it inherently would have to race. It can't possibly detect the fact that I'm in the middle of the section without introducing a data race. So you can reason in terms of these code sections as just executing in one block. You no longer have to worry about each thread executing just one statement. The basic implementation model behind all of this is that by similar reasoning, if we look at things between synchronization operations, any chunk of code between synchronization, nobody else can tell no other thread can tell what's going on there, because that would introduce a data race. So the compiler is allowed to optimize those sections as though it were a single-threaded piece of code, essentially. Not quite, but close. Synchronization operations need to be careful about what they do and need to make sure that neither the compiler nor the hardware reorders things in bad ways around synchronization operations. So let's talk about data races a bit more, because I think that's actually the key to programming correctly here. If we want to write a correct C++ program, multi-threaded C++ program, basically, in order to argue that the program is correct, we have to go through 2 steps. We have to first show that there are no data races. And in order to show that there are no data races, we can use this naive interleaving-based semantics. That's exactly the right model to use when reasoning about data races. Once we're done, we can then, in order to show that the program actually does what we want it to do, we get to assume not only the interleaving-based semantics that we had before, the simple model that we had before, but because we know there are no data races, we also get to assume that synchronization-free regions, these regions of code without synchronization operations, are indivisible. They look atomic. So let's look at some examples for data races here to really understand what they are. So here's a common use of incorrect, really badly incorrect use of a data race, actually. So let's assume that there's some variable x that I'm setting in thread 1, and then I'm setting the done flag to true when I'm done setting it so that other threads can use it. And the other thread waits on the done flag just by looping. And at the end, it should see x equal to 42. This does not work. It's a data race on the done variable, unless I declare done specially, as we'll see. It's a data race on the done variable. In real life, it very often doesn't work because the compiler will just decide that done is a loop invariant variable, will read it once, and then loop on the result, which means that either the while loop either will not loop at all or it'll loop forever, which is not very useful. So this is one of the few examples that actually tends to break repeatably in practice. So here's another example. This one breaks much less frequently, but it's quite common in code. This is sort of a simplified version of something that's often called double-check locking. This one actually doesn't check twice, it only checks once. But so if I want to make sure that something is initialized before I use it, but I want to initialize it lazily, I don't want to initialize it ahead of time, the correct way to do that is I can acquire a lock, check whether it's initialized, or one correct way of doing is I can acquire a lock, check that it's initialized. If it's not initialize it and release the lock, and then use the variable. But that can be somewhat slow because I acquire a lock every time I access this variable. So what people often do is they have a fast path check outside the lock that checks, is it initialized? If it's not initialized, acquire the lock. Either to check that it still hasn't been initialized, or in this case here, if the initialization can be done repeatedly without ill effect, just initialize it again. And then after that, go ahead and access the variable. This has a data race on this flag initialized. This is not correct. This is actually one of these examples that often works in practice, but it's not reliable. There are compiler optimizations that will break this, legitimate compiler optimizations that will break this, or hardware optimizations. So here's an interesting one that actually confuses people very often. And when we started this, we sort of asked this in all sorts of circles. It turns out it also confuses standards committees fairly regularly. So here's a simple program, and let's assume that we're given that x and y is initially 0. Does this contain a data race? Well, maybe unsurprisingly, a lot of people say yes, because clearly the same variables are mentioned on both sides. But in fact, if you think about it, there can't possibly be a data race here, because in any sort of interleaving-based execution of this, no variable is ever assigned. So we can't possibly have a concurrent access and assignment. Remember, x and y are initially 0 here. There's no interleaving that will ever execute one of these assignments. So there's no data race. And it actually turns out that's important. If you try to define a data race so that this doesn't work, more complicated examples end up really weird. So here's another one. If we have two small fields that are next to each other in a selector class, and we assign them separately in each thread, does that introduce a data race? It turns out it introduces no data race under C++ 11 or C11 because these are sort of separate objects. They're technically separate memory locations, and that's fine. On the other hand, many older standards, in fact, allowed this to introduce a data race because somehow these fields are too small to fit into separate memory locations. And there's some really old hardware on which it's actually difficult to implement this correctly. So under the older POSIX rules, which I think are similar to ancient Windows rules, this actually was problematic. Under C++11, it's not. On the other hand, if I change these to bit fields here, and this is a little bit of a subtle point, in fact, this does result in a data race because the C++11 rule is that any contiguous sequence of bit fields actually acts as a single memory location and therefore can interfere with accesses to other bit fields in that sequence. And for those of you who are familiar with the implementation strategy here, you'll see why that's done. The problem is it's common to sort of read both fields, update one, and then write them both back in order to implement the bit fields. When you do that, two threads can interleave in such a way that one update can get lost. If I have one bit field and one ordinary field, there's no data race in C++11. That actually requires some mild, though not very expensive, implementation heroics, which a lot of compilers don't implement correctly yet. So there's officially no data race, but don't do this quite yet. Let's look at libraries a little bit. So here another couple of interesting examples. Let's assume that we have one thread that pushes something onto the front of a list and another thread that tries to pop something off the front of a list. Is there a data race? Well, the definition of a data race actually talks about sort of basic scalar objects. It doesn't talk about things like lists and vectors and so on. It talks about ints and pointers and stuff like that. On the other hand, the way libraries are generally designed in C++11, and usually the way I think you should design your library, is that you should get a race on scalars. You should get a race according to the language definition, if and only if precisely when there's a high-level race on the library objects. So if you have one thread reading a particular library object while another thread is writing it, that's a data race, and the library is allowed to have a data race there as well. If the library under the covers needs some shared data structures which the programmer doesn't know about, then the library needs to be careful to use mutexes or whatever to make sure that it doesn't introduce any low-level data races where there aren't any high-level ones. Okay, and here's if I didn't tell you the answer, this would be a trick question. So we have a different setup here, and this actually gets back to the question of why I told you not to use some of the thread primitives at the beginning. Let's say we have thread 2, which sort of acts as a server and occasionally looks at this list X, and if there's something in it, it processes it, and it does this forever, which means that it really can't be joined by the main thread. It just goes on forever. Now, the main thread occasionally adds something to this list for the other thread to process. So does this have a data race? Well, in fact, both of the list accesses are protected by the same mutex. So there's actually no data race between the actions in thread 1 and thread 2. However, there is a data race here. The reason that there is a data race is that thread 2 goes on forever, and at some point the list X has to be destroyed. So what happens here is we introduce a data race between the destructor of X and thread 2. And it turns out that data race is fairly unavoidable for code like this. So that's in fact why I'm giving you the advice not to use thread detach, which allows you to create threads that run forever, or that run for an unbounded amount of time, because these data races are very difficult to avoid. Here's another trick question, if I didn't give you the answer. So this is really Baroque code. We thought, until people told me they actually wanted to write stuff like this, but that often happens, I guess. So I want to initialize X, and when I'm done with it, I want to tell another thread that I'm done by acquiring a mutex. This is a really stupid thing to do. Never do that. The other thread can wait for me to finish initializing X by basically trying to acquire the lock. If it can acquire the lock, clearly I'm not done initializing, so it just loops. It unlocks it and tries again until the lock fails. Once the lock fails, it concludes that thread 1 has acquired the lock, and therefore x must be 42, so it checks. So the thread 2 checks that x is in fact 42. This can fail. And the standard actually intentionally sort of presents you with a simpler explanation than the truth here. The way to think of this is that try lock may fail spuriously, and that's essentially what the standard says. The reality is slightly more complicated here. Try lock is actually not likely to fail spuriously, but it turns out that in order to make this work correctly, we would have to, for memory model reasons, we would have to make lock much more expensive, and nobody wants to see lock much more expensive. So there's sort of a subtle line of reasoning, but the way to really think about it is that try lock can fail spuriously, and so long as you take that into consideration, your code will be correct, in which case it's obvious why this has a data race, because the while loop here may terminate prematurely, in which case the assertion can execute while x is still being assigned 42. So I told you that there were actually two ways to prevent data races to first order approximation here. Mutexes and atomic objects. The motivation for atomic objects is actually fairly clear if you look at some of the existing code. For example, if you look at pthread's code, pthread's code actually, it turns out, also is not allowed to have data races. It also invokes undefined behavior with data races. So we didn't invent that approach. Actually, Ada83 had the same approach. So even POSIX didn't invent it either. On the other hand, pthread's programs very often actually have intentional data races. And if you talk to people, they say, well, this is it's much too slow to do anything else. Introducing a lock there is much too expensive. So the motivation for atomics in C++11 really is to remove this excuse that told people, that basically allowed people to introduce data races even though they really knew they weren't supposed to. So atomic objects, if you declare a variable as an atomic, it allows concurrent accesses to that variable. It's essentially exempt from data races. On the other hand, by default, you still get the nice interleaving-based semantics, which means the compiler has to do some work. Before I look at the C++ specific issues here, C++11 specific issues, I should warn you about naming, which is a mess, especially if you deal with more than one language. So there are a whole bunch of similar primitives in different languages. So in C++11, usually you'll use the atomic template. There are also specific atomic underscore int, atomic underscore long, and so on types. In C11, they're the same atomic underscore types, so that worked out well. It turns out that there is also an analog of the C++11 templates, which couldn't work out well since C11 has no templates, so there's a different syntax for that. It turns out that if you also program in Java, then Java has volatiles and java.util.concurrent.atomic, which has sort of which also have very similar, though not quite identical semantics. So these are all sort of the same, and they're often referred to as synchronization variables generically. The related constructs, which are sort of similar but still different in profound ways, are things like C# volatile or OpenMP 3.1 volatiles. And what's officially completely unrelated, if you look at the standard, though in fact for sort of reasons of being able to deal with existing implementations is often drawn in here, are C and C++ volatile, which really means something else officially. So I forgot to change the title there, sorry, that should have been 11. So C++11 atomics basically have sort of the operations you expect. All of them define load and store operations on the variable. You can atomically access one and assign to it. They sort of define the convenient syntax so that most of the time you can actually use a conventional assignment syntax and everything will just work. They overload operator equal. and they have an appropriate constructor to essentially implement the load. They also support compare exchange and exchange operations. If you don't know what those are, for now, we'll leave it at that. If we look at the sort of integral and pointer specializations of those, they also add atomic increments and the like. They do not add atomic to atomic assignments because that would have been confusing because it actually implies two separate atomic operations. So we didn't put that in. On the other hand, that's one place where C11 is actually incompatible. So if we want to implement a counter with atomic objects, this is the simplest way to do this. You just declare the counter x to be atomic int rather than int, and you say x++, and things just work. The increment is atomic. If we write Decker's example using atomics, we can write it as before. We're now exempt from data races, and in fact, it's the compiler's job to make sure that everything works as though we had interleaving-based semantics. So R1 equals R2 equals 0 is actually impossible. The compiler and hardware have to do whatever it takes to make that true, which can be fairly heroic. If we wait for a done flag, we can do that the same way. The only real race here was on the done variable. If we declare that atomic of bool rather than bool, life is good, at least the first order approximation here as far as we're concerned. Everything works. Similarly, for lazy initialization, the initialized flag is the only thing that has a race on it. So if we make that atomic, then again, things are fine. The problem is I mentioned that, in order to implement these things, to preserve the interleaving-based sequentially consistent semantics, requires some compiler and hardware heroics here, and those can be expensive. So in fact, I'll mention briefly that C++11 also has some lower level primitives which relax these interleaving-based constraints and tell you I don't really need, basically usually make things run faster. On the other hand, they no longer guarantee that things behave as though the individual actions were interleaved, and they make it much harder for you to actually reason about what the program does. In fact, usually what makes these really difficult to use is that if you use them in a library, it's very often difficult to isolate that effect to the library. So the library calls themselves may no longer look as though they were simply interleaved either. So the client may have to worry about this. It's hard to hide this stuff in a library. So these things are far more complicated and error prone. So use them with great caution. On the other hand, they do sometimes make things run faster on current hardware. I think many of us are actually interested in trying to convince processor vendors to make that less and less true over time, but certainly currently that's still true. So if you really want to take advantage of these low-level primitives, for example, you could write the done flag example in another form, which is likely to be faster but much harder to read and much harder to reason about in this form. You can say, well, when I assign true to done, I actually don't care about certain kinds of memory ordering properties. In particular, I don't care whether actions that occur later in thread 1 actually look like to other threads like they were performed before setting the done flag. So it's okay. I'm going to relax that just in order to make it go fast. And similarly, when I check the done flag, I can explicitly specify this sort of reordering constraint that the compiler has to obey in order to make the code correct without slowing it down any more than necessary on the hardware. So concluding here, C++11 is finally a multi-threaded language. The Threads API actually does leverage C++ language features correctly. So it's much easier to use than using the pthreads API or something like that, or the Windows Threads API, though it's also significantly less flexible. No matter what you use, whether you use the C++11 API or some pre-existing API, we finally have clean semantics for shared variables, which avoid some of the ongoing issues between compiler writers and users that we've seen in the past about what exactly these things mean and what properties compilers need to guarantee. Atomics are there to make it easier to write data erase-free programs, so it should now actually be possible at minimal performance loss, especially if you use these really low-level atomics, which are really tricky to use, but no harder to use than the hardware versions of these that people used before. The sort of catch-fire semantics for data erases that is used in C++11 is actually a very nice tool at the moment, I think, in that programs really should be data erase-free anyway. You don't want to write programs containing data erases. And this gives you a nice way of leveraging that. It's also convenient from our perspective as designers of the standard in that we don't have a clue as to how to define the semantics of data erases. Unfortunately, neither do other languages which have to, like Java, for example, for security reasons. So we actually have a solution to this problem, largely because we can get away with leaving things undefined. On the other hand, I mean, leaving things undefined here is not completely perfect in that if you actually introduce a data erase bug in your program, you don't have a lot of tools to work with. Basically, we've just said the compiler may have done anything whatsoever to your program, so the result may not be particularly comprehensible. In practice, that's probably not that big a problem, but it's certainly a place where there's room for improvement. So essentially, you should think of data erases here as out-of-bounds array accesses in C or C, out-of-bounds C array accesses. All bets are off, and really, you should avoid using them. OK, thank you. There's some references here. I listed a range ranging from those that are more easily understandable to those that are sort of very mathematically rigorous. Any questions?
Right over there. Yeah, I was curious about the atomic operations. So does that guarantee no reordering of the atomics, and does it provide guarantees of the proper publishing so that all CPUs see the stored results?
If you use the default version of atomics, where you don't explicitly specify memory order, it does guarantee that. So it guarantees sequential consistency. You can reason as though the threads were interleaved.
OK.
So it guarantees all those nice properties. The compiler has to do whatever it takes to make that true.
I see. And then it properly publishes then so that all processors see the stored result? Or
well, all processors see the stored result in the correct order. There's another question of sort of progress guarantees of sort of when they actually see the result. And the standard is very weak in specifying that, both because we don't know how to specify it and because the hardware is also often very weak in specifying that.
OK, so it's not guaranteed then?
Yeah, we should look at a specific example. I think it does guarantee what you want unless you're worried about something like real-time behavior or, I mean, technically even termination properties. So that's all real implementations will do the right thing there.
OK,
great.
I guess I didn't get the question answered then. I know if I use synchronization methods like mutexes, I can guarantee that when I unlock, that other processors will correctly be able to load and receive that result.
But again, it's really an ordering property, because once you unlock, when another thread acquires the lock, it's guaranteed to see the values that you wrote.
Correct.
And you have the same property for atomics.
Oh, OK.
But there's no guarantee that when you unlock the lock, that within n microseconds or something, the other processor will be able to acquire the lock.
Right.
So there's no such timing guarantee or anything like that.
No, I understand. Thank you.
The standard doesn't allow data races now, thanks a lot for that, but it doesn't enforce this rule in any way. Is there anything that standard can do or does already to help race detectors? Thank you.
The standard does very precisely define data races, and we know how to write dynamic data race detectors that will sort of detect all races that were not ordered in a particular execution. So there are tools you can write that will warn you if anything bad happened in a particular execution. The downside with those tools is they're currently way too slow. So there are, in fact, many people looking at sort of research solutions to that, but we have nothing that I foresee making it into the mainstream in the next few years. Oh, okay.
We have a race. We have a race. You can tell me which one.
Okay.
You mentioned that a way to avoid data races is to use locks and atomics, but locks themselves can have issues. Like if you employ them on a wide scale, you might end up with deadlocks, which might be just as worse as a data race.
That's certainly true. That's a problem for which, I mean, currently the C++11 solution is the one that everybody else tells you with locks, is that you should make sure that lock acquisitions are suitably ordered and so on, so that you don't have deadlocks. I would be the first to agree with you that that's not a perfect solution, and in fact one of the things we're proposing for the next iteration of the standard is to look at transactional memory and atomic sections, largely to try to address this issue. But it's not something that's currently solved in the mainstream in any way.
Will you also look at immutable data? Because that's the way that functional languages tend to solve this issue. They just avoid locking of any kind because they just copy the data.
You certainly have the opportunity to do that as well. And in fact, we have, I mean, C++11 atomics were in some cases motivated to a significant extent by that sort of implementation. So there are sort of very specific ordering constraints which, if you really want to use the low-level atomics, that were designed specifically to make that sort of thing fast. So it is, as in with most things in C++11, you have many ways of doing things, and certainly that's a perfectly acceptable solution.
Thank you.
Yeah, give it to the one who lost the last race. I guess this will be the last question.
So I'm trying to understand one of the examples related to data races, the structure with two cars. And you said that there is no data race, A and B. If one thread writes to A,
this one.
Yes, that's the one. So I'm trying to understand from a compiler point of view. So unless the variable is atomic or volatile, the compiler is free to create stores, to synthesize stores, to anything, right?
The compiler, sorry, I didn't understand what...
The compiler can create stores to any memory, right? Unless it's volatile.
The compiler, in the C++11 memory model, the compiler in general cannot create stores to any memory location, because that would introduce data races, visible data races, which introduce weird behavior for programs that have perfectly well-defined semantics under C++11.
So that's exactly my question. So the standard explicitly says that a compiler cannot. So the compiler in some cases may read a value and write it back to the exact value.
This is not allowed unless an assignment to that variable was there in the source. If the assignment to the variable was there in the source, then the compiler can reason that there would already have been a data race. Therefore, introducing another store to that variable is OK. But it cannot introduce a store spuriously to a variable that was not previously assigned.
OK, and this is new in C++11, right? This restriction is new in C++11?
This is, in some sense, this is new in C++11. It was... you can argue about whether it was there in POSIX already, but a lot of compilers did it the other way. You're right. The problem with doing it the other way is I can show you examples where the compiler will break your code in ways that you couldn't possibly have predicted.
Okay, that's exactly the reason I'm asking that, because I'm working on the compiler, so I'm trying to make sure that we understand exactly what we cannot do. So it sounds like with C++11 that's not legal. It's clearly not legal to do that.
C++11 you cannot do this, but it's clearly defined.
Okay, thank you.
Okay.
Destruct.
All right. Please, Hans.